In a previous video we looked at a function of two variables x and y where f of x comma y equals z. It's the z coordinate of this point here. We looked at df, that's the infinitesimal change in the function for infinitesimal changes in x and y. So we consider this nearby point whose coordinates were x plus dx comma y plus dy. So we were after taking limits here. Let's suppose that we had not taken limits. So now the change in x is not some infinitesimal quantity. It's some very small quantity, but it's not infinitesimal. Then the coordinates of this point will be x plus delta x. So delta x is the change now, and the change in the y coordinate is y plus the change in y. Let's call that change in y delta y. So delta x and delta y are very small, but they're not infinitesimal. Now what about delta f? Well, that's the vertical difference between these 2 points. So z is corresponds to this point here, and this point here will be up here somewhere, and this difference here we will call delta z or delta f. Okay, so how do we get delta f in terms of delta x and delta y? Let's consider the slope of the tangent to the surface at this point. But we want this tangent to be in a plane parallel to the xz plane. So we're getting the rate of change of f with respect to x, the rate of change of the function in the x direction. So we want the slope of this green line here. Well, here's the green line. So we know its slope is the partial derivative of f with respect to x, evaluated at the point with coordinates x comma y. Since we are not dealing with limits here, this blue region is not quite a parallelogram as we saw in the last video, so its sides could be curved. Let's look at the slope of the tangent line in terms of delta x. That's the horizontal distance between this point and this corner of the region, this corner here. So the x difference, I should say, not distance, because distance is always positive, but a difference could be positive or negative. Delta x doesn't have to be positive. So here's delta x. It's just the x difference. Now we can approximate the slope of this tangent by this distance here divided by this distance here. Now I will call this vertical difference delta z. Now it's not the delta z we're after. We're after the equivalent of df or delta f. That's actually the difference between the f or z values of these 2 points. So this is a different delta z. But since the slope of a line is rise over run, we can approximate this by delta z divided by delta x. So you can see that for this difference here, we can use this as an approximation. So this is for this side of the region, but for the other side of the region we can do something similar. I won't go through it all now, but we can consider the tangent line to the curve at this point here, and when we're talking about these 2 points, the delta z for these 2 points can be approximated by the rate of change of f with respect to y. That's the slope of this blue line here. So this blue line is in a plane that's parallel to the yz axis, and we can multiply that by the change in y. So that's the difference in the y values of this point and this point here. So this point here is y plus delta y. So these are 2 different delta z's. We're dealing with the difference in the z values of these 2 points to get this one, and the difference in the z values of these 2 points to get this one here. And we saw in the previous video that if we add those two together, we'll get an approximation to the difference in the z values of these 2 points. We proved that using vectors. So now we're after delta f. So we just sum these two. So this expression here will give us an approximation to delta f. It's the difference in z values of these 2 points when we are not taking limits. If we take limits, of course, we get this expression here. It's worth looking at the derivation of this. It's in the previous video. Now delta f, which is nothing other than the difference in the value of the function between a point xy and a nearby point x plus delta x, y plus delta y, is given approximately by this quantity here. So let's take this example. Well, we need both of these partial derivatives. Delta x and delta y, as I've said already, are small values, but not infinitesimally small. So we need the partial derivative of f with respect to x. Well, we treat y as a constant, so we get 2x plus 3x squared y. Then we need the partial derivative of f with respect to y, or f sub y. Differentiate this with respect to y, x squared goes out. So we just have a constant times y here, so we get that constant, which is x cubed. Well, we treat x as a constant. So what do we do then? We multiply df dx by delta x and df dy by delta y. Now the smaller we make delta x and delta y, the better this approximation is. Now this here is the absolute error of our function at any point x comma y. And for small values delta x and delta y, it doesn't matter what those small values are. Now suppose we want the absolute error of this function here at a fixed point minus 1, 2, and we are given the small values delta x and delta y. Well, we do the same as before. We have to calculate f sub x, or partial derivative of f with respect to x, and then we have to calculate fy for this new function. Difference here is we just have to plug in this point. So this is delta f for a general point xy. So we just have to plug this in, plug minus 1 in for x, 2 in for y. And we're given values for delta x and delta y. As you can see, they're quite small. So here are the partial derivatives. Differentiating with respect to x means we hold y constant. So we get 2xy squared for this term. 1x becomes 1, y goes to 0. Differentiating with respect to y means we treat x as a constant. So we get 2x squared y here. We get 0 for this term, and we get 1 for this term. Here's the absolute error expression, and we just plug in the values. For delta x we plug in 0.1, for delta y we plug in 0.025. Now delta x and delta y don't have to be positive. They happen to be positive in this example here. Now as for x and y, well, that comes from the coordinates of the point. Plug minus 1 in for x, plus 2 in for y. This becomes minus 7, this becomes plus 5. So we found an estimate for delta f. Now, how do we get the exact value? Well, we just evaluate the function at minus 1, 2, and then we evaluate the function at the nearby point. Now, how do we get the nearby point? Well, we add delta x onto minus 1. That's going to give us minus 0.9 actually. And we add delta y onto 2. That's going to give us 2.025. So the nearby point has coordinates minus 0.9 comma 2.025. So there's the actual error delta f, the difference in the function at those 2 points. So you can see that they're reasonably close. This value compares well with this value.